to computer. All right. Okay, so let's go ahead and get started here today talking about the second chapter in our syllabus, which is atoms, molecules, and ions. So we're going to do a little chemistry now. Chapter 1, not very much chemistry. But now we get into the chemistry. Okay, so we're going to begin with the atomic theory. And the atomic theory is based on the following idea, that if you look at matter, so for example, if you take a glass of water, so you have this little glass, a cylinder, and it's full of water, that if you analyze what that water is composed of, you will find that it's made up of little atoms, which are essentially little spheres. They're spherical, so like little balls. And they're connected to each other. And the smallest unit of water, so I'm going to put a little box around this to suggest that this is the smallest unit of water. So if you make it any smaller, if you break it up into any smaller pieces, it's no longer water. That it looks something like this. It looks like it has one large ball in the middle and two smaller ones connected to it, okay? And that if you then break that up into even smaller pieces, so you break these two up like this, so now they're individuals, right? So they're no longer part of it. And then this one is separate over here. What you would find is that this one right here in the middle is something called oxygen. And that these two over here are something called hydrogen. Okay. And so these individual little particles are called atoms. Okay, so this would be an oxygen atom, and these would be hydrogen atoms. And those would be the smallest units of hydrogen and the smallest units of oxygen. Okay, those are atoms. So when those three atoms combine, they make something called a molecule. And this molecule is what we would call water. So the substance, water, is comprised of these molecules, which have one oxygen atom attached to two hydrogen atoms. So there's three of these atoms in a water molecule. And what we find is that much of the matter that we have on the Earth is comprised of these molecules. So for example, there's a substance in the atmosphere called carbon dioxide. Carbon dioxide is comprised of an atom in the center with two atoms connected to it. So these atoms that are connected to the central atom are called oxygen again. So there's that oxygen, right? And then the one in the center is carbon. And so each of those individual particles are atoms. So this one has three atoms, right? Two of them are oxygen, and one of them is carbon. So carbon dioxide, right? So that whole thing together is called a molecule. And the individual particles that make up that molecule are called atoms. And it turns out that in nature, there are around 90 to 92 of these different types of atoms. Okay. Let's see, let me save that one and open up another one. So anywhere from 90 to 92, depending on how you count them. Naturally occurring atoms. But we don't call them, in this sense, atoms. We call them elements. Okay. So the couple of them that you're familiar with hydrogen, right? That's actually the simplest element or the simplest atom that exists in nature. And we'll talk in this chapter about the structures of atoms so that we can understand what a hydrogen atom is compared to an oxygen atom. And since there's a lot of them, 90 to 92 is a pretty large number, we're going to go ahead and use a symbol for each of them. So the name of this element, the simplest element in nature, is called hydrogen. And the symbol for that hydrogen is a capital H. The second most simplest element is called helium. And since the name starts with an H, we got to give it a different symbol. So we'll call it He. So these symbols that we use for the elements have usually either 1 or 2 letters. Okay, so H for hydrogen, He for helium. The third one is lithium. You've heard of lithium in terms of lithium batteries, right? Li. This is one maybe you haven't heard of, beryllium. Be. Boron, you maybe have heard of. You've maybe heard of borax. Borax is used as a cleaner. Oops, sorry, I spelled borax. I meant to spell boron. Capital B. Okay, so beryllium is Be, boron is B. Carbon is the next element in our series. Let's put it that way. We have a series here. Capital C, C for carbon. Nitrogen. So these are ones you've heard of. Capital N. Oxygen. You've definitely heard of oxygen. Capital O. Fluorine. Maybe you've heard of that. You've heard of fluoridized toothpaste, right? That's fluorine. And neon. You've heard of neon lights. Right, so there's Ne. So those are the first 10 elements in what we call the periodic table, or our series of elements that are found in nature. The history of these elements is fascinating and is something that scientists study even to this day. All of these elements that are here, with the exception of hydrogen, have been created within stars, and that's the amazing thing. It wasn't known even back in 1920. So that's not that long ago. That's 100 years ago. 100 years ago, they didn't know where these elements came from, to be honest with you. But it turns out they come from stars. So hydrogen is the simplest element. It was formed in the Big Bang. Once the universe was expanding and cooled off to a temperature that was low enough, hydrogen could become stable. We'll talk about the structure of atoms later. Those hydrogen atoms, over periods of time, started attracting each other through gravity, until there were enough of them that you could form what's called a star, which is just a huge agglomeration of hydrogen atoms. And what happens is, if those gravitational pull is strong enough, those hydrogen atoms can combine with each other. They actually fuse together and release energy. The process releases energy. And, oh, Tosca, you having a problem here? You have no sound? We have a couple of other people here. Anthony, can you hear me? How about
I can
you?
hear you. I
You
can
can
hear you
hear
loud
me.
and
Okay,
clear.
so Tosca, it might be your situation. So you might need to log off and then log back on. Okay, maybe that's the issue. Okay, so in these stars, like our star, our sun, we call it, right? Hydrogen atoms right now are fusing together to form helium atoms. And when that occurs, it releases energy, and that energy works its way through the sun until it just escapes the sun in the form of sunlight. And some of that sunlight is very useful for us. Photosynthesis, it keeps the atmosphere of the earth warm. We love it, right? Some of it is very highly energetic and dangerous, but our atmosphere blocks a lot of it out. And we have a magnetic field on the earth that makes it kind of, a lot of that high energy radiation goes to the north and south pole instead of hitting the surface of the earth. So we're protected by certain properties of the earth that allow us to survive. But that helium is being formed over time. Eventually what will happen is the sun will convert essentially all of the hydrogen into helium. And when that happens, that process will stop. but then the helium will start fusing and forming lithium. And so a heavier element will get formed out of that. And then lithium gets converted into beryllium, and then beryllium gets converted into boron. And that's so the stars, as they age, they go through different cycles, and carbon, nitrogen, oxygen. So what we know is that our own sun already has beryllium, it already has boron, it already has carbon. So we have to ask, okay, well, if it's making that stuff, but it already has it, where did that stuff come from? And it turns out it came from a previous generation star. So all the carbon that we have on the Earth, all the carbon that the sun already has, and the other planets in our solar system have, came from a previous generation star that probably blew up at some point, 6 billion years ago or 5 billion years ago, however long it was before our sun started. And then those elements rained out into space. Over time, gravity brought them together to form a new star, which is our own sun, and the planets that make up our solar system. So scientists are still trying to learn about that process. They're studying other solar systems using astronomy, using telescopes, but they're also collecting rocks in our own solar system. We have satellites that go out and grab a little bit of a comet and then bring it back to Earth so that we can study it and figure out this process, how solar systems form. So those elements all exist now. And then, as I said, there's around 90 to 92 of them. These ones that I listed here are that's just the first 10. There's other ones as well. So for example, you're probably familiar with iron. Iron is what we use to make steel. And it has a funny symbol, right? It's not IR. You might think it was IR or I. But iron is actually Fe because some of the elements have been known for a long, long time. And in the past, we used other languages to describe them. So iron, Fe is actually ferrum, which is a Latin word.
Levan.
You've got nickel.
Levan, why are you looking at Sharissa?
Come over here. Oh, let's do participants. Funny how that works. Okay, all right. Nickel is Ni. Gold you've probably heard of, right? Gold. This is one of those older ones. It's aurum, so it's Au. There's silver, Ag. Okay. So copper, Cu. These are all metals, right? These are, we'll talk more about them as well, but these are all metals. Okay. Uranium. This is oops, sorry, I didn't put the symbol. This is probably the heaviest element that's formed in nature. So it does exist. It's in the crust of the Earth, so it already exists. So produced probably from an explosion of a supernova. And but anything beyond that is not actually exist in nature. So as I said, there's 90 to 92 naturally occurring elements, but there are now 118 known elements. Okay. And those 118 known elements include the 90 to 90. The reason I say 90 to 92 is that there's a couple of elements that you can find them in nature, but they're very rare. They're just hard to find because they're not very stable. But the total number is around 118 because there are some that are made in laboratories. So they don't last very long. They might only last for less than a second, but they can be made and they can be produced. There's some that last longer and have certain uses, but in nature, the ones that are known are around 90 to 92 of them, okay? So those are called elements, and the elements are, there's just the terminology here. The elements are these individual materials. So I could say I have helium, that's an element, but the helium that we have is made up of atoms. So the atoms refer to the individual particles of an element. And in general, they do have sizes. They have different sizes. So for example, a hydrogen atom is the well, actually, it's not the smallest. A hydrogen atom is small. Helium atom is actually a little bit smaller. So helium's a little tiny bit smaller. So they have sizes, and an oxygen atom is bigger. And let's take an iron atom. An iron atom is even larger than that. So these can actually be measured. We can measure the sizes of atoms using X-rays and determine actually how large they are, and actually measure it out to like 3 significant figures, okay? So iron, uranium is even larger. Now notice they're not that much larger, right? It's not like it's 10 times the size, but they do get bigger. Okay. So, but if you think about it, if you look at them, they're essentially little balls. They're little spheres, right? So that's one thing that we've learned using modern techniques is that atoms are essentially little balls or little spheres. And so it's useful for us to use these symbols to represent these atoms. So for example, carbon dioxide, which I mentioned just a moment ago, right? It has the carbon in the center and then 2 oxygens surrounding the carbon. Notice I made the oxygens a little larger. Oxygen's a little bit larger than carbon, okay? In this structure anyways, and for reasons that you'll go over in later courses. So there's carbon dioxide. So it gets a little tedious writing out the whole name. It's not useful to write out the whole name often. So what we do is we use what's called a chemical formula. So the chemical formula, what we do is we indicate how many atoms we have of each element and then use the symbols. So this would be CO2. So if you see, so this is the symbol of carbon, right? That's called a symbol. This is the symbol for oxygen. The whole thing together is called a formula. Okay. So, you think about it this way, like if you're watching some old movie, some old horror movie where they give some concoction to someone and then they turn into a monster, right? They would give them a formula. Here's the formula to turn that person into a monster, right? So CO2 would be called the chemical formula for carbon dioxide, and you're going to use it a lot. The formulas are important. One thing that you want to remind yourself about a chemical formula is that if there's only one atom of an element, you don't write any numbers. It's just like, for example, it doesn't say C1O2, it just says CO2. So if you have in it, there's no 1 there, that just means it's 1 atom. Okay, this would mean there's 2 atoms. Okay, so for example, water, right? H2O. We don't say H2O1, we just say H2O, meaning that there's 2 hydrogen atoms and 1 oxygen atom. Okay, and sometimes you can figure out the arrangement of atoms, but sometimes it's not that easy. So that's one of the things we learn how to do in the next course, Chemistry 1100, is how to figure out the arrangement of atoms from the formula. It's not necessarily easy to do that, okay? But you'll learn how to do that a little bit. The more chemistry you take, the more you'll learn how to do that. Come back over here.
No se le llama eso.
I don't know why. Sometimes it's hard to do this. There we go. Alrighty. Okay. So let's take a look at an example then. So I'm going to look at an Aleks problem where we're essentially just counting the number of atoms. So just counting the number of atoms in a formula unit. Okay, so we have a chemical formula and we want to figure out how many atoms are in that formula. So the one that they show here is for trisilylylamine. Okay, and the formula is given as SiH3. And then there's parentheses there, and then there's a 3 outside the parentheses, and then there's an N. Okay, so in this particular example, what we're going to do is we're going to count the number of silicon atoms, hydrogen atoms, and nitrogen atoms in the formula unit, okay? So notice those parentheses. The parentheses are important. The parentheses are written there as a shorthand notation to tell you that everything that's inside the parentheses, there are 3 of them. There's 3 of everything that's inside the parentheses. So it's SiH3, 3N. So let's go through it. I'm going to start we'll start with silicon. So inside the parentheses, there's only 1 silicon, right? Remember, if it doesn't have a number, that means there's 1. So there's 1 silicon in the parentheses. However, there's a 3 outside the parentheses. So that means there's 3 of everything that's in here. So if you have 1 silicon on the inside, but then there's 3 on the outside, that would be 3 silicons. So you got 3 atoms of silicon. The hydrogen, there's 3 on the inside, but there's a total of 3 of everything that's in the parentheses. So that would be 9, 3 times 3. So that would be 9 hydrogen atoms. And then the nitrogen is outside the parentheses, okay? So if it's outside the parentheses, you don't have to worry about that 3 that comes before it. So it's just 1, right? Again, if there's no number written for something, that just means it's a 1. So there's only 1 nitrogen atom in that. And let me show you what it actually looks like in terms of atoms. Let me put the nitrogen. This is something you don't need to know in this course, but it's something you go through in the next course. Essentially what happens is there are 3 silicons attached to the nitrogen. Okay, so there's your 3 silicons. And then on each silicon, there's 3 hydrogens. Kind of cool. So trisilylamine. Amine means nitrogen. Okay, so again, you don't need to do that in this course. This is something that you would go through in the next course, but that's essentially the meaning of it. So just kind of deconstructing it, you got a nitrogen, there's only 1 of them. You've got 3 of these SiH3s. So look what I did, SiH3. See, that's 1 SiH3 right there. There's a second SiH3. There's a third SiH3. So that's why the numbers work out the way they do. 1 nitrogen, 3 silicons, and then 3 times 3, that would be 9 hydrogens. Okay, so you'll see those parentheses quite a bit. They come up a lot because the formulas can get pretty complicated, and so we need to be able to represent those formulas in some sort of shorthand notation. Let me see if there's any others that you might want to look at, or I might want to look at here. Well, that's weird. That's the same one. Okay. Let's try one more. So here's the chemical formula, NH42, and then CO3. Okay, so for this one, let's just count the number of hydrogen atoms. All right, number of hydrogen atoms. Okay, so here's hydrogen. So notice it's got a 4 there. So that means there's 4 inside the parentheses. The 2 means that whatever's in the parentheses, there's 2 of them. So if you have a group of 4 atoms, but there's 2 groups of them, that would be 4 times 2. So you just say 4 times 2. And so that would give you 8 hydrogen atoms. Okay, everything else is pretty simple. The nitrogen, you've only got 1 inside the parentheses, but again, you got that 2 outside there, so it'd be 1 times 2. So you've got 2 atoms there. This one's outside the parentheses, so you don't have to worry about the 2, it's just 1. And then the oxygen, right there, there's 3 of them. Okay, by the way, the term for the numbers down here is called a subscript. So when we get to ions, you'll see stuff like this. This is called the subscript, sub meaning under. And then the number up above is called a superscript. Okay, so far we're only dealing with subscripts. We haven't dealt with superscripts. We'll get to them when we get to ions, but that's a subscript right there. That's a subscript right there. That's a subscript right there. Okay, subscripts are called. Okay, let's see here. Okay, next we get into the issue of the structure of the atom. Okay, so let me escape here. I don't know why it's taking up so much space. Let's talk about the structure of the atom. Now, there are different ways of talking about the structure of the atom. We're going to look at the simplest model to begin with. And so remember, all these elements are made up of atoms. So a carbon is carbon is an element, but it's made up of individual carbon atoms. So there's carbon atoms. Each of those is a carbon atom. And now what we're going to do is we're going to look at the structure. What is that thing made of? Okay. It turns out it's important because if we know the structure of an atom, we can kind of make predictions about how those atoms will interact with each other, how they'll react with each other, what they'll form when they react with each other, that sort of stuff. So we want to have some information about that. Okay. The general picture that we're going to have is that you have this central region here. This is the center of the atom. Okay. And then outside of that central region are particles that you can think of as going in motion around the atom, around the center. Kind of like a solar system. In fact, it's been called the Planetary Model because it's sort of like a solar system. So at the center, we call this the nucleus. The nucleus is the center of the atom. And that nucleus has two different types of particles. It has protons. So this is inside the nucleus. And protons, the symbol for a proton is a P, and it has a positive charge. Okay. And it has a mass that's approximately equal to 1 AMU. And we'll talk about AMUs a little bit more technically later on, but it has a mass. So in the center of the atom is this thing called the nucleus, which has protons in it. And the symbol for the proton is a P. It has electrical charge. It's a positive electrical charge. And it has a mass. The proton has a mass of around 1 AMU. Okay. But there's a second type of particle in the nucleus. It's called the neutron. And they have a symbol N, and they have no electrical charge. So you don't have to worry about the charge with the neutron. In fact, the word neutron means neutral, doesn't have electrical charge. But they also have a mass, and their mass is about an AMU. Okay. Now, outside the nucleus are these particles which are called electrons. So I'm going to draw them as little balls. They're actually not little balls, but we can draw them that way. And these are called electrons. Okay, notice I've drawn a few of them. Now notice they're not all in the same spot. Unlike the nucleus, which is just one little central region, the electrons are in different locations. Okay, you can think of them as just kind of like planets around a star. So think of the nucleus like the sun, and then you can think of these little electrons kind of like planets going around it. The electrons have negative charge. And they have a mass which is really small. It's approximately 0.0005 AMU. It's a really small mass, okay? The symbol for the electron, I'm sorry, I didn't give you the symbol. The symbol for the electron is typically a little e with a negative written as a superscript. Isn't that cool? Okay, so there's 3 particles. There's 2 that are in the center, which is the neutrons and the protons. And then there's the 3rd particle, which is the electron, which is outside of the nucleus. And just to give you kind of a sense of scale, this picture doesn't really give you the sense of scale. Here's an analogy. If we thought of the nucleus as being the size of, like a little marble, okay, a little marble, like a little toy, about that big, then the position of the electrons would be like the outside of a stadium. Imagine a stadium where you can fit 50, 60,000 people. So imagine a little marble at the center of the field where the game is played, and then the electrons would be way out at the edge of the stadium, like thousands of feet away. So very, very large region of space. So the planetary model is, in a sense, it is a little bit like a planetary model of a solar system in that you got the sun at the middle, but there's a lot of space until you get to the planets, much larger than the size of the star of the sun until you get to the next planet. Okay, so 3 types of particles. And so the total mass of an atom is just equal to the sum of all the protons, neutrons, and electrons. So you just take the number of neutrons plus the number of protons plus the mass of the electrons. Okay, so let me show you an example here. This is an Aleks problem. Let's take a look at this one. It's using this kind of picture here. Let's take a look what it says. So in this example, they give you the name. Well, they want you to find the name, and then the symbol, and then the charge, and then the mass, and then the location. Okay, so here's what they do. They say, hey, you've got part A here, and then you've got these orbits out here, and then this is B out here, and then there you go. Okay, so they just want you to label certain things in here. Okay, so they tell you some of the information in this table, and then other things they don't tell you, and they want you to fill out the table. Okay, so I'm going to make 3 rows here. So they tell you that right there is -1, and then your mass, 0.0005. This is in the units of AMU, and then the location is B. So they give you some information for that one. In the second row, they give you some information. Okay, and then you have to figure out what the mass is here. And then they have to tell you the location. Oops, sorry. Dun, dun. Okay, so same thing here. You have to figure that out. So here they only give you one piece of information. And then the last one, they tell you the charge is 0. Oops. 0. And then they give you the mass. So again, they're giving you some information for each of these. And then you have to figure everything else out. Okay, so let's take a look at this one. Let's start with the first row. So they want you to give the name of this. They tell you it's in location B. So that means it's out here. If it's out here, those are the electrons, right? The particles that are on the outside are the electrons. So we just call this electron. Okay. The symbol for the electron is an E with a superscript negative. Okay, so when you're doing this problem, make sure that you use the little superscript function for Aleks. Aleks has a little thing when you enter in the answer, it's going to pop up where you can like pick the superscript, and then you put the negative as a superscript, and then that'll allow you to do that. They already told us the charge is -1, so that makes sense, right? As we said, the electron has a charge that's negative, so that's correct. They already told us what the mass is, 0.0005, so that's correct. The electron is 0.005 AMU. And it's already in location B, so we're set. So we know that already. That's all done. Let's go to the second one. Well, the second one, again, they tell us the symbol. So they're telling us it's an electron. we already know that that's the symbol for an electron. So they're giving us everything we need to know. That's an electron. The charge of an electron is -1. The mass of an electron is 0.0005 AMU. We already know that. And the location, hey, the electrons are out here. So that's location B. So we've got that one too. The third one is, okay, let's see what they give us. They tell us the charge is 0. That's the giveaway right there. There's only one out of our 3 particles that has a charge of 0. That's the neutron. This neutron means no electrical charge. It's neutral. So that's got to be the neutron. The symbol for the neutron is just an N, lowercase n, not M, N. And charge is 0. They already told us the mass is 1 AMU. They already told us location is A. Yep, that makes sense, right? The nucleus is where the neutrons and protons are. Okay, so there you go. So you can fill out that table. Really, all you need to know is one piece of information. If it's an electron, if they tell you its location B or they tell you the mass, the electron, everything is different from the proton and neutron. The things that's the same for the proton and neutron is they're in the same location. They're both in location A. So if they just gave you location A, you wouldn't know if it's a proton or neutron. But if they told you the charge, the proton's +1 or 0, that's got to be a neutron. So not too difficult, kind of fun. Fun filling out the charts. Okay.
Professor?
Yes.
So any number that they give you aside from -1 or 0, then it will be a proton.
So here's the one thing that could be the same. The neutron and proton, they weigh about the same. They both weigh about the same. So if they told you the particle was 1.0 AMU, that's how much it weighs, you wouldn't know which one it is.
So
you'd
then
you'd need another piece of information to figure those ones out.
Okay.
So that's usually electrical charge. So usually what happens is they tell you it's, 0 charge or +1 charge. So for those 2 particles, you got to know something other than the mass.
Okay. All right. Thank you very much.
Mm-hmm. Yeah, they're fun. Those ones are fun. You'll enjoy that. So that's called the planetary model. And that's, even though in the next course we'll build on that and show you that it's a little more complicated than that, it's not a bad way to think of the atom, is just having these 2 parts. The center, which has the protons and neutrons, and then the outside part, kind of like planets, right? Those are the electrons. The electrons are negatively charged. And it's important to note that the stability of the atom is that since all the protons are in the center in the nucleus, right? All the positive charges in the nucleus. That's where the protons are. The electrons are outside that, right? So the electrons are out here. So essentially what happens with an atom, it's just electricity. It's a very simple thing. It's electricity. Those electrons are negatively charged. The protons are positively charged. And when you have particles with opposite charges, they're attracted to each other electrically. Okay. So what happens is, like, if you on a winter morning where the air is dry and there's no humidity, so the air is dry, if you run your comb through your hair, you can get the situation where the hair is attracted to the comb. And the reason is the hair has an excess amount of electrical charge, and the comb has the opposite electrical charge. So the comb might have extra electrons, so negative, and the hair has extra, positive charge. So they're attracted to each other. So the hair will hold up, it'll stick toward the comb, right? That's called electrostatic attraction. And it's due to the fact that if you have substances that have opposite charges, they're attracted to each other, okay? So the electrons being out here, and the protons being in here, that gives you a stability because the electron is not going to leave that proton very easily. You have to pull the electron off. But the atom is going to be stable because the electron is just kind of attracted. Just, the Earth is attracted to the sun using gravity, right? It's gravity that causes the Earth to be attracted to the sun and vice versa. But for the atom, it's actually electrical charge that drives the process of the atom, okay? The neutrons and protons are also attracted to each other, but that's a different force. It's called the strong nuclear force, which we just don't even really worry about in chemistry. It's not an issue for us. Okay, so the next thing is to take a look at counting particles. By the way, these are called subatomic particles because they're smaller than the atom. So our subatomic particles are the proton, which has a charge of +1, and it has a mass of 1 AMU. Our second subatomic particle is called the neutron. It's an N. It's got no charge at all, no electrical charge. And then it also has a mass of 1 AMU. By the way, they're not exactly the same. The neutron weighs a tiny bit more than the proton. We'll get to that when we do later in chapter 2, we'll deal with that. They're not exactly the same, but to two significant figures, they're the same. Then you got the electron. All right, those are the ones out here. That's an E with a negative, and then it has a charge of -1, and then it's got a really, really small mass, 0.0005. Okay, so in this particular type of problem where you're doing your counting all of these particles, protons, electrons in an atom. Okay, so let's do this. Let's do the calcium. I'm just going to pick calcium. Okay, now here's the thing. You cannot answer that question. So how many protons and electrons are in a calcium atom unless you have access to the information. So what you do is you look up the periodic table. Just Google it. Now, Aleks has one, so you can use the one that's on Aleks. That's perfectly fine. But if you just Google the periodic table of elements, you can get the numbers. So what you do is you look up the table and you just look it up for calcium. So let me do this. I'm gonna come up here. Actually, you know what I'm gonna do? I'm gonna stop share, and I'm gonna try to bring one up for you, just so you can see it. Is this one gonna work? The problem, the only issue with Googling this is that there's so many bad periodic tables that are hard to see. It's sometimes hard to find the right one. So let me come over here. I'm gonna do images. It used to be good. Like when you Googled the periodic table, you get a nice one that would just pop right up. But so many people put stuff on now that it's hard to find a good one. And then so many of them are really meant for like elementary school kids that they don't have the information you want. Okay, so here's one. So let me share the screen here just so you can see it. Okay. There we go. So now you can see that, right? So there's an example of the periodic table of the elements, okay? So there's different pieces of information that we'll be interested in using in this course. For right now, there's only really two pieces of information that we need. And the first one is the symbol, right? So if we are looking, for example, for carbon, carbon is up at the top. It's in a lavender color on the right side of the periodic table, there. Let me just hide my pictures of myself here. Okay, so if you look at the top left corner of each of those squares, it's got a number. So the one starts at the top on the left side is hydrogen, and that number we're looking at is at the top left corner. So it's a 1, right? You see for hydrogen it says 1. And again, you know, a periodic table is not a, you know, it's not like a patented thing. So it's not the same everywhere you look. Whoever types up a periodic table, they have a certain amount of creative control over how they make it. So there's going to be differences. So the nice thing about this one here that I chose on Google is it actually explains everything that's in it, right? So, you know, up at the top, it says nitrogen is an N. That's the chemical symbol. It gives the name of it underneath, nitrogen. And then there's a relative atomic mass at the bottom, 14.007. And then the atomic number is in the left side. It says 7, okay? So for now, when we're counting protons and electrons, the number that you want to refer to is the atomic number. The atomic number is the number of protons in an atom, okay? So if we're looking at nitrogen, nitrogen is atomic number 7. That 7 is the number of protons, okay? So for the example we're looking at calcium. Calcium is element number 20. So that's in the 4th row. So you start with hydrogen, then there's lithium, that's the 2nd row. Sodium, number 11, is the 3rd row. Potassium is the 4th row, K. Next to potassium is element number 20, and that's calcium, okay? The symbol for calcium is Ca, capital C, lowercase a, and the number is 20. So that's what we're looking for in these problems, is the atomic number, which is the number of protons, okay? So let me see if I can share here, and we'll see if that pops up. Okay, all right, well, we lost our screen here, but that's okay. All right, so what we want to do is for calcium, we want to count the number of protons and electrons. Okay, so let me write the little square here just so you can sort of see it the way it was in that periodic table that I showed you. So it gave you the name, and then it said 20 here. Okay, so that's your atomic number right there. And the atomic number is the number of protons in one atom. Okay, so calcium has 20 protons right there, that number there. So calcium has 20 protons. Now here's the nice thing about this particular problem. In an atom, the number of protons is equal to the number of electrons. Isn't that cool? It's perfectly balanced in an atom. And so if we have 20 protons, we also have to have 20 electrons. Perfectly balanced. Okay, so an atom is a balanced object. It's a balanced particle. It has the same number of protons as it has electrons. That's kind of cool. So if we were to do another element, let's say we were going to do iron. Okay. All right, let me go ahead and stop share. Let's come on back over here to, oops, our periodic table. Okay, if we were going to do iron, we had to look it up, right? So you look it up, you look for iron. Iron is right in the center, left, right. It's in that gray region. That gray region are what are called transition metals. These are the metals that you're familiar with in terms of industry. These are the ones that we make our cars out of, we make our airplanes out of, we make our phones out of. Those are the transition metals. So iron is right there at 26, Fe. Right? Remember, some of them are in Latin. So Fe for ferrum is actually iron, and it has an atomic number of 26. So see how the numbers go from going from left to right, they increase from left to right. So 26 is iron. Okay. Okay, so iron is element number 26. The symbol is Fe, right? So the number of protons, very simple, 26. The atomic number is the number of protons. Electrons, that's also very easy because it's going to be the same. In an atom, the number of electrons is perfectly balanced to the number of protons. So there you go. So you got both of those numbers. Now notice I didn't tell you how many neutrons there are. That wasn't in the question. That's a different type of question, is how many neutrons are in there. To figure out the number of neutrons, we need a little bit more information. So that's why that's not in that question. Okay. All right, let's do. Here we go. Let's take a look at that. Okay, so now to get the number of neutrons, as I said, you need another piece of information. We need one more piece of information to answer that. And for that, we have to deal with something called isotopes. So it turns out when you make atoms, when a star makes atoms, this all occurs in stars. All the atoms that are in the universe, with the exception of hydrogen, are made in stars. When that happens, it's possible to get different forms of the same element. So for example, carbon, it's actually possible to get 3 different forms of carbon. One that has 6 protons, 6 electrons, and 6 neutrons, neutrons. And we call this carbon 12. The 12 comes from adding the protons to the neutrons. We add those 2 numbers together. So 6 plus 6 is 12, right? Not the electrons. Ignore the electrons for this. So that is formed in stars. But stars are also able to make a second form where there's 6 protons, 6 electrons, and 7 neutrons. Okay, and we call that one carbon 13. Why? 6 protons and 7 neutrons. Remember, those are the 2 particles that are together in the nucleus. So all we're doing is we're adding up the particles that are in the nucleus to each other. So 6 plus 7 will be 13. And in nature, there's a third one. Now, you can't very easily predict these. We just have to study them and figure out what these stars make. But they exist on the surface of the Earth. They exist in our body. There's a certain amount of each form of carbon in our body. And 8 electrons. I'm sorry, 8, sorry. I'm trying to do this a little quickly because I don't want to go over time. 8 neutrons. So again, what you do is you add the protons, 6, and you add to that the neutrons, which is 8. So you get carbon 14, right? That's called 14. These are called isotopes. So when you see that word isotope, what it's referring to are different forms of the same element. Okay, different forms of the same element. So how do those forms differ? Just by the number of neutrons. Okay, so that number 14 or 13 or 12, it's referred to as the mass number. And the reason they call it the mass number is because a proton and a neutron weigh about the same. Again, they don't weigh exactly the same, but they're pretty close. They both weigh about 1 AMU. So if you add up the number of protons and neutrons and each one weighs 1 AMU, then the total number is just going to give you the mass number because each one weighs 1, right? So I would say that carbon 12 weighs about 12 AMU. Carbon 13 weighs about 13 AMU, and carbon 14 weighs about 14 AMU, okay? So let me show you an example. It's very simple. So in the Aleks problem, what they do is they say, hey, how many protons, how many neutrons are in one atom of, and then they give you the symbol here. Ag109. So at first that might look a little daunting when you look at it, but it's actually very simple. Here's what you do. You look at the symbol Ag. So you look for that symbol. By the way, this is silver. And again, we don't have to worry about the number underneath it at all. Ag is right here, 47. Okay, so that's your starting point. Again, you go into the periodic table. Again, that's your atomic number, right? So that's the number of protons right there. You got the protons right there. So 47 protons. That's how many protons one atom of silver has. You also have electrons. This question, they don't ask you for electrons. They just ask you for protons and neutrons, but we could get that. That's easy, right? It's the same. In an atom, the number of electrons is equal to the protons. So we got that one. But what about the neutrons? Here's what we do with this one. It's not in here. This just gives you the number of protons. And that's why I said you needed one additional information here. That number right there. That's called the mass number. It's kind of cool. So here's how you deal with this. 109 is equal to the number of neutrons plus protons. That's what the mass number tells you, how many there are together. So we already know that this is 47. Right? We already know that. So how do we do this? Okay, well, we know that 109 equals the neutrons plus 47. So just subtract 47 from both sides. Okay, so 109 minus 47 is what? 59, 62. Yeah, 62. And then 47 minus 47 is 0. So that'll give you the number of neutrons. And there you go. So we got our third one, 62. You can check it and just make sure. You take the protons and you take your neutrons, you add them together. So 47 plus 62 is 109. So perfect. There's our mass number right there. It's as easy as that. So that's a standard type of problem that you'll see. Let me show you one more example. Okay, let me see that one. Actually didn't. Okay, so here they give you BE10, and they ask you for the number of protons and neutrons. Again, you can get the number of electrons very easily because once you find the protons, it's equal to the electrons. So BE, you look that symbol up. Be is beryllium. So probably the most difficult thing in this problem is just going through the periodic table and looking for the element. But here's a little tip. That number kind of gives you a sense of how big the number is going to be, where you're going to look for it. So if that's a small number like 10, it's going to be at the beginning of the periodic table. It's not going to be at the end. It's not going to be way down. It's going to be up pretty high. So if this was like, 100, then you would go down. But if it's like 5 or 10 or 15 or 20, it's going to be up kind of high. Then you find beryllium, and you find that beryllium is element number 4. Okay, so there's your, again, it's atomic number. Okay, so the atomic number is the number of protons, so that's a 4. They tell us the mass number, right? So 10 is the mass number. And the reason they picked that name is because each of these particles weighs 1 AMU. So if you know the number of particles, that essentially gives you the mass. It's approximate. So here's what we do. The mass number is 10. That's equal to the number of protons and neutrons. Okay, we already know the number of protons is 4. So you subtract 4 from both sides. So that's 6. So now we know the structure of this particular isotope. 6 there, right? And again, this problem doesn't ask you for electrons, but the previous one did, right? So you can still find that. That's going to be 4. And so you've got that number, okay? So isotopes, these are the same element, but different mass number. Okay. And then you've got this thing called atomic number. And that's equal to the number of protons. Okay. So if you look at this right here, the mass number is going to be written after. The atomic number is not going to be in there, but there is actually, we'll probably get to this notation. You may see, if you look things up, you may see something like this. In this symbol, what they do is they put the atomic number down here. And then they put the mass number up here. So you'll see that too. That type of notation also exists. Okay. So you have the symbol for the element. And then you have the atomic number down here at the bottom. And then you have the mass number up above. Okay. So the number up above should be at least as large as the one that's below, because this is equal to protons plus neutrons. So it's got to be at least equal to 4. Okay. Can't be smaller. And there you go. Okay. Let me see if there's, oh yeah. So the next topic, which we'll talk about in next week, is 2.4, which is all about the periodic table. So I gave you kind of a little introduction to it today, but we'll talk more about the periodic table next week. And then once we go over the periodic table, we'll start doing more kind of precise calculations of atomic mass. We'll look at atomic mass and get into that. But for right now, the main thing you want to look at are the isotopes. And feel free to work ahead, though. You can certainly work on the periodic table. It's easy stuff. It's high school stuff. We won't get into the more difficult calculations till later. Okay. So have a great week. If you have any questions, reach out to me. And I do have office hours during the week. Generally, the way I deal with that is you just contact me, get in touch with me, and we'll work out a time that works for both our schedules. Okay. So have a great day.
Thank you, Professor.
Thank you, Professor.
Absolutely. Bye-bye.